Okay, let me start. So first of all, I would like to thank the organizers for inviting me to give the talk here. And yeah, I really enjoy my stay at Jerusalem. And I know all of you are tired, so let me try to finish it as soon as possible. So anyway, let me start. So I'm going to talk about the probing topology from wave function in theory and experiments. So the seminar, the talk is about the simple question that how do I probe the topology of the band topological states in theory or in experiments. For example, in the theory, I would be interested in the states beyond the band theory. And this talk is based on a few parallel and PRBs, and although the main references are going to be just these four. So let me start with a brief introduction of the topological states, even though we heard about it a lot. So this is a single slide summarizing the topological insulators. So topological insulator is a phenomenon of the quantum mechanical electrons moving in the solid. And although there are a lot of stories and theories, I'm not going to tell it, but I can just briefly remind you the phenomenology of the topological insulators. So the topological insulator is just a state which is whose bulk is insulating, but if you go to the edge or boundary or corners, they tend to be gapless, which are protected by symmetry, like Yoshi Avron introduced symmetry protected topological states. This is one phenomenon. And sometimes they come up with the quantized dissipationless responses like the quantum Hall states. But the points that I'm going to tell you is that these states are not always easily detected, and direct detection of the topological insulators in theory and the experiments are not always straightforward. So let's just start with the experiments. So what do we do to probe the topology? So let me start with a simple example, which is a Schuster-Higger chain, which is just dimerization of the atoms in the real space. So this is x-axis. And the simplest way to detect it is to cut it out and then make an open boundary. Then you will see the edge states. So if you do the calculation in energy, and then if you look at the energy spectrum, then these edge states tend to be in gap in the idealistic case. And so it's quite amenable to detect in STM experiments. For example, we did so with the experimental colleagues, we also see that some variation of the Schuster-Higger chain. We also detected the edge mode through the STM experiment. But the question I would like to ask is if it's this easy in general. Actually, this is not the case. So, for example, in the Schuster-Higger chain, the edge modes actually in the realistic situation tend to hide very easily into the bulk spectrum. So, for example, let's say I have an open chain, and then I apply the boundary perturbations, then the edge modes tend to hide inside the bulk spectrum, and these modes is not very easily detected in the experiments. By the way, these kind of perturbations doesn't change the bulk topology, so detection of the topological states, even in this simplest case, is not very clear in the experiments. The situation gets worse when you go to the higher order topology.
When does this happen?
Yeah. So I just so this is a theoretical calculation. So we added the reflection symmetric potential at the boundaries. Then because these edge modes are zero-dimensional object at the boundary, so if you add the boundary perturbation,
it's really a sharp end of the chain.
yeah, but you can spread it, and then that's going to also absorb into the bulk. The situation is worse. Yeah, but I have a reflection symmetry, and reflection symmetry is enough to define the topology for the Schuster-Higger chain. Yeah.
But with the reflection symmetry, the edge mode is not bound to be at zero. That's what you say.
Yeah, correct. Yeah, thank you for the clarification. The higher order topological insulators, like the Younguk showed before, or in our another papers, people look at the corner states where you need a clean corner with the crystal symmetry. But if you are an experimentalist, you are going to say this is impossible, right? The sample edges tend to be dirty, and the corners, the corner states are not always coming from the topology, so it could be just accidental. So the corners are not always sharp in experiments, and the localized modes are not always associated with the topology. So even if the theorists say that there is a higher order topology, it's not very clear how to detect it. That's the problem with the experiment, and in the theory, there is another issue. So let's look at how the people theorize about the topology of the topological insulators. So what people usually do, at least in the textbook, is you consider the band picture of the topological insulator, where you consider the free electron with the lattice translation symmetries, like electrons are hopping around nicely, and you are solving by the type binding calculations. Then you get the eigenstates, which is given in terms of the block states, and using the block states, you can calculate the topological band index like Zak phase that the Yoshi introduced. Then they are typically certain functions of the block functions. So the problem in this whole setup is you need free electrons and the lattice translation symmetry. But if the topological state is really a robust phase of matter, then you expect it to survive against the disorder or interactions. So for those cases, what should I do? So those are the questions I asked almost 3 years ago, and then I tried to answer with a few papers. So I'm going to start with what do I do for the generic insulator in theory? How do I probe the topology? And then I'm going to go to the versatile tool to probe the band topology in the experiment. So I believe the experimentalists are more patient than theorists. So let me start with the theory. At least all of my experimentalist friends tend to be more patient than the serious ones. I'm not inserting you or you, but yeah, anyway. So let me start with the main reason about the theory. So our proposal to detect the topology without band picture is following. So I need to consider the many electron ground states with a certain magnetic flux inserted into the state. And then I'm taking the ratios of the certain overlaps of the ground states with some unitaries inserted in between. So I'm not going to explain all these why, but this is formula I found. And this ratio will tell you the topology of the states you are considering. And this unitary, I'm going to be clear soon. And the unitary will be specific for the target band topology that I'm going to consider. And this strategy seems to work pretty well for a broad range of the topological states, including the polarizations, multipolar insulators, Chung insulators, chiral hinge insulators, axion insulators, and boundary polarizations, and or the generic 2D corner states. And then there are other series. The motivation for this, as we heard before, nothing is new. Nothing could be new. So the motivation for our formula started with Restas conjecture on the Zak phase that the Yoshi introduced briefly. So the paper goes back to the 98, and what Resta conjectured, it has never been proven. What he conjectured is that you can calculate the polarization using the ground state, which is actually many electron ground states prepared on the ring of size L, like periodic boundary conditions. And then if you take the overlap with a certain unitary operator, which goes like x to the number operator, then you get the polarization. Actually, for the free electron, you can prove it's really the polarizations because you can calculate this one in terms of block states. Then you find the Zak phase that we encountered before. So this actually showed a way to calculate the band topology without any reference to the band structures. So I'm going to show the similar formula, but I would just want to show you why this could be possibly a good approach before doing any calculation. So why this could be a good approach? First of all, as I said before, if the topological state is really a phase of matter, then you expect to be robust against interaction and disorder. So it's natural, it's kind of natural to consider the many electron ground state, which you can define even in the case of the interactions and disorders. On the other hand, we know that the topological states typically pump something under when you thread the fluxes. So it's kind of natural to consider the flux inserted ground state and then compare it with the states without the flux. Then with these intuitions, the last question you need to ask, so then what should I do with this ground state? So for that, what we found is to calculate this. So I'm not going to go through all the examples, but let me focus on at least one example, which is Chun insulator, which is kind of like one of the most famous topological states, including the Schuster behavior. The Chun insulator is characterized by Hall conductivity, which is given in terms of the integer c divided by 2 pi. So for that, our protocol is following. So I prepare the ground state. This is theory, not the experiment. So I prepare the ground state on the torus, and then I thread the flux along the x direction a little bit, like for example, like 0.01 times 2 pi, and then I consider the operator that Resta considered. Then what I can prove is that the ground state overlap with this operator with the flux and without flux. Then the ratio between them gives the Chun number. And actually, yeah, you have a question?
Can you go back one slide?
Yep.
So I just wanted to check whether this operator y is well defined on a torus.
Yes.
Why?
So if you
Is it periodic or what?
yeah, it's periodic along the Ly. So y shifted by Ly, you get the number 1. So yeah, so this is well defined.
Okay.
Yeah, yeah. So in our paper, we found at least 3 different ways of prove this formula. Actually, we found another after publishing the paper, but it looks like there are many different ways of proving it. So for the series sitting here, let me just walk you through a little bit. Experimentalists, I know you're patient, so keep patient a little bit more. So for that, what we calculate first is I just remember this overlap. According to the Resta, it's given by some real number times the phase factor, which is given by the polarization. So then this ratio, I think even the experimentalists can do the division. I'm sorry, I didn't mean to. But if you do that, then you see 2 pi I, py pi x, which is coming from that, and this minus sign is because you are dividing by that. And because phi x is small, you can now perform the like the Taylor expansions. Then you get the 2 pi I phi x, dpy, and d phi x. So if you are familiar with the quantum Hall physics or the like Chun insulators, then you quickly notice this is the Hall conductivity. Actually, you can calculate it. You can actually prove it. And then if you plug the c over 2 pi, which is Hall conductivity, then this formula just gets the 2 exponential I phi x c. And there are other more beautiful ways of proving it, but I'm not going to delve into it and just show you the numerical demonstration of the formula. So for example, I consider the simple free fermion model on the scale lattice, and this model has a free parameter m. So when m is bigger than the 2, then the Berry curvature formula tells you the Chun number is 0 or 1, minus 1. When the m is 2 and 0, and between the 0 and minus 2, you get Chun number minus 1, and m less than minus 2, you get 0. And then our formula, if I plug the electron ground states, then you get the consistent answers where m less than minus 2, you get 0, which is consistent with that, and m minus 2, between minus 2 and 0, you get minus 1, and 1 and 0. So actually, you can test our formula even for the interacting models using the like DMRG, and then you can easily check it works well. Okay, Chun insulator could be too trivial, and then actually we can go to the like chiral hinge insulator, which is more recent version of the Chun insulator, which is a 3-dimensional insulator. This is a real space picture. And in the chiral hinge insulators, there is a chiral mode going up along the hinges in the alternative way. So this insulator can be viewed as adiabatic pumping of the quadrupole moment. And about that, we can actually construct the many-body operators using the operators similar to the Resta's formula, except that I have x, y, and the number operator. And then if you plug that, then you can show that this is a band index. And for the model, which is known to support the chiral hinge insulators, you can show that the phase diagram is correctly reproduced, which is kind of like proving our formula.
Can you just tell me what's a chiral hinge?
Yeah. So this is a three-dimensional insulator where the edge mode of the quantum Hall states is living only on the hinge. Yeah. And then this insulator can be viewed as kind of like adiabatic pumping of the quadrupole moment in the momentum space. It's like quantum Hall states is adiabatic pumping of the polarizations. Yeah. So with that, I would like to summarize the theory part. So we designed many different many-body invariants for the several topological insulators, including the Chung insulator, chiral hinge insulators. But in our papers, we show that it can be applied to Schuschel-Heger, quadrupolar insulators, axionic insulators, and so on. And they are related to the defining characters of the topological insulators, like the adiabatic pumping of something. And I didn't emphasize much, but this provides a numerically efficient, accurate evaluations of the topological invariants for the interacting systems. So with that, let me jump to the experimentalist part. So this part I would like to ask, is there any versatile tool to probe the band topology in experiments? So the answer I got is to use the Rix experiment. So Rix in a single slide is following. So you are shooting a photon to the sample, and then the photon will shake the sample, and then the photon comes out. And then it can transfer the momentum and energy according to the Fermi-Gordon laws. And what we noticed is that from the scattering amplitude or scattering intensity, you can directly access the topological band index. It's not going through the edge state. We are not detecting the edge mode, but we are directly detecting the band invariance. That's something we are going to see.
What is this?
This should be the resonant inelastic X-ray scattering. Yeah. So for the theorist, this scattering process is always characterized by the operator you insert between the initial state and final state. And the operator you are inserting for this Rix experiment is given by the local electron hole creations of the atom. Because basically the photon comes in and then it excites a local electron, leaving the local hole behind, and then the light goes out. So it transfers the momentum and energy to the atom. And then what we need to do is I plug this one and then calculate this amplitude and see where the band invariant is hidden. So to glimpse the possibility, let's take a simple example. So what I'm going to show you in a few next slides is that the Rix intensity is going to capture certain features of the wave functions. So for that, let's take a simple dimer where you have only two atoms, and then the electrons are hopping between them. And then we know that for this system, there are only two states. One is the bonding state and anti-bonding state. And the bonding state has a lower energy, and the anti-bonding state is higher energy. And and then I'm going to consider the scattering process where I transfer the momentum Q and the energy 2, which is the energy difference between the bonding state and anti-bonding state. So the initial state, you are starting with the ground state, but the final state, the Fermi-Gordon law tells you there is only one state, which is anti-bonding state. So what's going to happen is that when the scattering happens, the photon can touch the first atom or second atom. And when it touches the first atom, it's going to generate the factor e to the I qx1, where x1 is the position of the first atom, and then e to the I qx2 when it touches the second atoms, and then it's going to relax back to the anti-bonding state eventually. What's actually interesting here is that what we observe is only the initial state and final state, and we don't see what's happening in the middle. And these two processes will appear in the same way in the scattering process. Okay, I start to see all of you are getting tired, so let me speed up. So, in the end, the scattering amplitude. Should I slow down? Okay, sorry. Yeah. So the scattering amplitude in the end comes with the e to the iqx1, which is the position of the first atom, and the e to the iqx2 with the second atom, but with the -1 sign, where the -1 sign, if you do the calculation, actually coming from the phase difference between this first atom, the antibonding state and bonding state. So from these simple calculations, you can calculate the intensity, which is just absolute value square of the amplitude. So why is it interesting? First of all, this simple picture is enough to explain the experiment data, which is done for the dimer. And they plotted in Q and then intensity, which sinusoidally oscillate. More than that, what we can easily glimpse here is that actually from the oscillation of the intensity, we can see kind of like entanglement between the sites where the electrons are living, or one can say that the RICS can extract the detailed information of the wave functions. And remember that the band topology is the property of the wave functions. So, and then this example is enough to see that the RICS can extract certain information of the wave functions. So probably it's useful to study the topological isolators. So let me, with these intuitions, let me show you the result. So let's go to our favorite model, which is the Schuscher-Perhiger chain, which is the simplest crystalline insulator with a reflection symmetry. And what I'm going to consider is the scattering process between the, so this is the band structure of the Schuscher-Perhiger model, by the way. So I'm going to consider the RICS transitions, which connects the gamma to the X, where the energy transfer, remember that RICS creates the local electron and hole, so you are creating the electron at the higher energy and hole behind the valence band. So I'm going to consider the energy, which is the difference between the X points of the conduction band and the gamma points of the valence band, and the momentum transfer is X minus gamma. So why this could possibly detect the Schuscher-Perhiger chain, the topology of the Schuscher-Perhiger chain? The reason is that the reflection eigenvalue of this, so the reflection eigenvalues between the gamma and X, when they are if you know them, then you can detect the Zak phase, which can take the either 0 or half. So you can easily see, if I know the scattering amplitude, then I can extract maybe the eigenvalues of the gamma and X. So is it actually the case? Actually, so you can ask that, and then you can actually do the calculation yourself because the model is so simple. Then the scattering intensity in terms of the momentum and energy goes like this. So you see there is some amplitude, like certain numbers, and sine square Q, which is momentum that I'm going to tell you a little bit more, and P pi, where P is actually the Zak phase. So if you tune the momentum and energy very nicely, then you can see that the intensity, scattering intensity, directly affects the band topology. And this Qn is 2 pi n plus pi, and so this is the size of the reciprocal vector, and pi is the momentum difference between the gamma and n. So RICS allows the large momentum transfers. So for the 5D elements, I was told that n from -3 to 3 can be easily scanned in the experiment. So you can actually do the scattering experiment.
So what's the meaning of D equals to 0?
D should be the distance between the A and B sublattice in the Schuscher-Perhiger chain. So D should be the distance between these two, something like that. Sorry, these two to that, yeah. So actually, if you do the simulation, then this is the result you get. So the green one is the RICS intensity of the trivial states, and the red one is the Rick's intensity of topological states. And I chose the parameter intentionally that the trivial states and topological states have exactly identical energy spectrum. And but if I calculate the intensity, then the green and red oscillate differently in the momentum space. So the x-axis is momentum and the y-axis is intensity. And so from the scattering experiment, you can directly detect the band topology. So is it only for SSH chain? So actually it's not. So let me skip a few. So actually you can generalize to the 2D quadrupolar insulators. So this is a higher, simplest higher order topological insulator. So you have 2D systems. This is real space. And then when you have corners, then there are like localized modes. So they have some realistic lattice models. Not realistic, sorry. There is a type binding model, but I'm not going to go through the details. But the point for this model is that the C4 eigenvalues at m point and gamma point, by the way, m is pi, pi, and gamma is 0, 0. So if you know the information about the gamma and m, then you can determine the quadrupole moment or topological invariance, which is either 0 or half. So from that, it's kind of like natural to consider the scattering between the gamma and m, and then I consider the scattering from scattering where you have electron at m and the hole at gamma. And I perform the numerical simulations for the trivial state and topological state, which also have the exactly identical spectrum. But you see that the two of them oscillate differently in the momentum. Actually, if you do the analytic calculations, then you can also show that the band topology, the quadrupole moment, explicitly appears in the scattering intensity. And this could be tested in the like germanium sulfur, germanium selenide, possibly which support the quadrupole moment. This can be also tested in the three-dimensional topological band insulators, which have the inversion eigenvalues. And so for these, actually the x point in the momentum space, so the topological band insulators on the diamond lattice, it's known that the x point is kind of crucial. So you can consider the scattering between the gamma and x. And this green one and the red one, they oscillate differently. And those are actually corresponding to the different combination of the inversion eigenvalues. And remember that if you can read off the inversion eigenvalues in the three-dimensional topological band insulators, then you can easily read off the Z2 invariant. So why do they work? So let me go. So why does it work? So this is a simple way to understand it. So let's take the Schuschel-Perhiger chain. Okay, Schuschel-Perhiger chain. And if you plug this simple scattering process into the operator and calculate the amplitude, the quantum amplitude, which you can find from your textbook, then this amplitude comes with the overlap between the wave function at gamma, the valence band, and the conduction band wave functions at x. And when you have reflection symmetries, you can ask how they constrain the form of the amplitude. And for that, you can just plug in the operators in between them and see how it constrains it. Then you are going to find this formula. So, yeah. Yes. So actually the process is like this. So let me explain in verse. So what's actually happening is that photon comes in, and then the core, the electron in the core level will be kicked out to the valence level. And you will have a core hole, but the core hole has a very short lifetime. So some electron in the valence bands will decay. And then that process is going to emit the photons. and that's going to leave you the one hole in the valence band and one electron in the conduction band.
I'm asking because you have low from gamma to X.
Yeah.
It is inelastic.
Yeah, it's an elastic process.
So you have a gamma application and losing energy to the photon.
Okay, so you go up, and then you hold down, then you need something else.
Yeah.
Okay, that's what I was asking.
Sorry.
Let's
Yeah.
say, oh, you hold down, so you go up, and then you hold down to the
Do you need a photon? I think
No, it doesn't need to be phonon. It's just yeah,
the photon.
yeah,
it's two photons.
yeah. This kind of approximation is known to be like fast collision approximation, which is kind of like
You control that the electron drops from the right value that you want.
I'm serious.
Pre-select,
So
post-select for this according to the outgoing momentum.
okay, so in the Rick's experiment, there are like you can control the polarization, which will select which orbital to be excited, and if you know like the for example in the topological insulator, S and P are important, so you can selectively excite the which state will be filled and which state can be empty, but there could be like other states which I cannot control. So in the actual simulations, we added some noises, which is and see if I can still fit it, and then actually it seems it's working. But yeah, I haven't seen any real experimental data yet. So, but yeah, we are going to do some experiments soon. So
And it's always between points of different symmetry on the Brillouin zone. It cannot be between points related by rotational symmetry or something.
yeah, they are going to be needed to completely determine the band invariant. Yeah.
What about if we don't have inversion symmetry?
Then I cannot do anything. So it's going to be applicable only for the crystalline topological insulators.
But can you change it into the version of the recent band without the information of inversion angle? Can you change the formula from the right
Oh.
side into the recent band formalism that doesn't depend on inversion symmetry?
Yeah, we tried, but we failed. Yeah, that's a good question, but yeah. So actually, the similar formula exists for the like other C4 symmetric 2D order insulators, chiral hinge insulators, and Chun insulators. And it looks like I can generalize to the topological superconductors too, but we are still working on it. So the simple message that that I want to convey is that the topological insulator is kind of like very particular X-ray grading, that the different topologies scatters the X-ray in a different fashions. So the topology manifests as like scattering patterns. So with that, I would like to finish with a few words. So how much time do I have?
8 minutes including.
Okay, yeah. Then the conclusions, I introduced the many-body invariance. Maybe I speak too fast, but the many-body invariance for the topological insulators, which can be applied to the Schur-Vehiger quadruple insulators, Chun insulators, and so on. And we showed that RICS could be a versatile probe for the band topology. But what you need is you need to carefully select the momentum and energy and the polarization of the photons too. So actually, because I have a little bit of time, so I would like to briefly tell you about the research of my group, which is like ending credit for my talk. Today what I told you is a little bit abstract, maybe too theoretical, but I also work with the experimentalists too. So recently with our colleague in my department, we realized the like steady flow case states. So in the flow case states, previously it was based on the like pump probe experiment, which survives only like 250 femtoseconds and so on. But here we used the like microwave. We realized the flow case states, which survives at least like 25 hours. And the upshot is that the microwave, we can flow case state has a like coupling constant, which determines how strong the flow case physics is, and that comes with the like amplitude of the electric field and divided by frequency. So previously, what people tried is to increase the electric field, and so that's why you need the like pump probe experiment. But here we decrease the omega, and and then reduction of the omega, you can actually reduce the heating, and so floquet states can survive longer times. And I also worked on the van der Waals materials, like the tantalum disulfide. We heard a lot of talks about tantalum disulfide. And I was interested in a particular system where the electrons are living along the one-dimensional wires, which are connected to each other, which seems to be relevant to the nearly commensurate CW state of the tantalum disulfide. And we also recently worked on some bilayer graphene coulomb states. And I also work with the string series. So, for example, friends from this other universities, we found that the topological states, the classification is similar to the mathematics used in the string theory, so which could possibly, hopefully, give the complete classification of topological phases. We are preparing one more paper which found at least 100 new topological orders. And like everyone else, we are also interested in the quorum simulators, and we consider some randomized measurement protocols which can be used in the NISC device to detect the characteristics like order parameters of the topological phases.
The session is open for questions. Yeah, go.
In the first part, you introduced this flux phi.
Yeah.
How do you introduce a flux to the SSH one-dimensional model?
Oh, yeah, thank you for the question. So actually for the Schuster-Perhiger chain, I don't need the flux. So actually for that, you can just use the Rastas formula, where you have only the ground state divided by ground state on the periodic boundary conditions. And then you are inserting the correct operator, then the phase factor knows the polarization. So you can do that without the flux. But even if you thread the flux, that's not going to change the physics. So.
Thank you. It was nice. I liked it.
I learned a lot from your papers, by the way.
Oh, thank you. You didn't stress it, but I'm sure you could point out that somehow it's important that one should either have a gap or there will be a mobility edge. You didn't comment on this. And the second question that I have is that usually when one discusses these topological quantum numbers, there is a difference in the object you look at in even dimensions and in odd dimensions. Right? In one case it is a Char number, in the other case it's some other. But you seem to give the formula that seems to hold always. Can you comment about this?
So for the first questions, I agree that there should be a gap. For your second question, I don't have a proof that it works for everything, but at least for the known examples, it looks like I can find the formula. So I don't know why I can find a generic formula for the known cases, but.
And it's always the same U. It's always e to the ix times the number operator, or some moments of the number operator.
Oh, so for that I need to be careful. So Chun insulators or quadrupolar insulators or the chiral hinges, those are requiring only the charge conservation. So it's enough to know the charge positions. But if I have other symmetries like time reversers and so on, then I need to a little bit modify the definition of the ground states and so on.
But what about U? U is always the same?
At least the cases I considered.
Thank you.
Possibly I could be wrong, but yeah, I will check it. Yeah. Thank you for the questions. Yeah.
In the last part, you mentioned that you can also use the Wicks technique for a Chern insulator, but all your examples were Z2, and this is an example of Z classification. So can you expand a little more?
Very nice question. So for the Chern insulator, I cheated a little bit. So for example, when I have C4 symmetry, from the C4 eigenvalues, I can determine the Chern number mode 4 or something like that. So I cannot read off the full Chern number, but at least mode 4, yeah. Which seems to be good enough.
It's interesting.
Yeah. Thank you. Yeah. at least I have never seen the experimentalists claiming that the realization of Chern number is Chern number 4. So, yeah.
Any other questions? Oh yeah.
Well, you have given a heuristic proof for this topological phase stuff by taking the Taylor expansion. What about non-small phi? Can you?
Yeah, then you need to use the topological field theory. So actually, you can rewrite this one as the partition function of the Chern-Simon theory, and then you are going to get the coefficient of a Chern-Simon term, which is C. Yeah, good question. Yeah, thank you.
Okay, I guess it's done. So let's stop here and thank the speaker again, all the speakers.